Yes, okay. So this work was done partly in collaboration with my old friend Robert Cocro from Marseille, and we wrote two papers. And so what is the problem? The problem is refinement of the problem that Carol was telling you about this morning, or rather it's another branching of the same problem of counting partitions. By partitions, I mean set partitions, okay, partitions of the set 1 to n, say. And each partition, I'm interested in its, what I call its type. I'm not sure it's the canonical word. Type being, so where do I press to have a pointer? Here? Here, yes. So the type is just the way of encoding the number of blocks of your partitions of a given size. Okay, so here alpha L is the number of blocks of size L. Okay, and so this notation is borrowed to the theory of classes of the symmetric group, for example, a Young diagrams, whatever. So such a partition of that type, I want to represent diagrammatically by a circle with endpoints and a certain number of vertices inside the circle. There will be alpha L vertices of type L, meaning of valency L, if you wish. Okay, and then also you want to connect the vertices to the external points. There will be no connection between, no edges between the vertices, only between the vertices and the external points, right? This is the rule. And also you want, excuse me, you want a map that preserves the cyclic order at each vertex. In other words, two edges emanating from the same vertex cannot cross each other. Okay, so they go straight to some point of the circle without crossing. Okay, so for example, that particular partition here is represented by a circle and 4 vertices, 2 of them being representing singletons, and 5 valency 5 and the valency 3 vertices. Okay, I think it's very clear. And now I claim that to such a diagram, to such a map, a map with that constraint, you may attach, you may associate a genus. So this is not a new idea, it's an old idea. I don't even know who was the first to make this observation. Myself, I'm quoting Walsh and Lehmann at the beginning of the 70s, but it may be even anterior. Anyway, so the formula is here. The formula is of course just a rephrasing of the Euler's formula for the genus of a surface, say. And here the number of vertices is clearly the sum of the alphas. There is a +1 because this circle could be contracted to a single point and making an additional vertex if you want to close the thing. And there will be the number of edges is clearly equal to n. And finally, there is a number of faces that you have to determine. So how do you determine it? Well, it's just a matter of being patient and following the circuits here. And if you do that in that particular example, you'll find that there are 3 faces. And the better way of seeing that is by using a notation of which the physicists are particularly familiar with, which is a notation introduced by 't Hooft, in which you draw all the edges as double lines. And then it's easy to just follow the lines and to count the number of faces. So if you do this little exercise, I claim that you'll find 3 in that case. Okay. So 2 observations before I go on. First observation is that it's that constraint that the edges coming from a given vertex cannot cross, which makes the calculation difficult. The consideration of the counting of these diagrams difficult. Otherwise, you have a variety of techniques that would use just ordinary maths. So it's that constraint which makes the problem non-trivial. Second constraint is that, second observation is that because the number of faces here is certainly greater than 1, greater or equal to 1, you have an upper bound on the number of, on the genus that you may encounter for a given n.
Excuse me, are these circles in 2 dimensions?
Everything is two-dimensional.
Okay. So they cross each other.
Excuse me?
The lines cross. Each other?
When they cross, in fact, it's no vertex. It's that. Well, okay. It's 2 plus epsilon. It's 2 plus epsilon dimension. Okay, they can avoid one another. Okay, it's no real crossing. You're right. Thank you for making this point. All right. So now the problem is to count this number the number of excuse me, the number of such diagrams of a given order and with a certain type and a certain genus. Okay, that's my problem. Now the sum of the genera is known. It's one of the numbers that well, in fact, no, sorry. For given alpha, that's a classical problem, and these numbers are the so-called Fadi Bruno coefficients. Those coefficients that you encounter when you make multiple derivatives of a composed function. Okay. So, but what we want is to find these numbers for individual g's. Now, to do that, I'm going to introduce generating functions. In fact, first generating function is something that will depend on certain indeterminates, kappas, kappa n's, and that will be associated with the vertices. So kappa n will, in fact, encode vertex in my previous graph, in previous slide, a vertex of valency n. And the numbers Cgn alpha are encoded into generating functions that I've written here. So Zg will have a term of 1 for genus 0, and then a generating function as well. So contrary to Carol this morning, I'll be happy enough if I find an explicit expression for the generating function. I won't go on to the next step of writing explicitly these numbers, right? So that's my goal, in fact, to find these generating functions. Oh yes, I forgot to say, when I'm writing things in that way, the kappa alphas here is just the product of the kappa L's, the individual indeterminates for the different classes of alpha. Right. So, why am I interested in that? Well, first, an observation, trivial observation, is that these things are natural and well known in the context of statistical mechanics and free probabilities. So in ordinary probability theory or statistical mechanics, I would call kappa L the Lth cumulant. The Mn would be the moments of a certain random variable, and the relation that I was writing before is just the classical moment cumulant relations, right? Now, when you go to when you fix the genus and go, for example, to genus 0, which is the most well-known case, then you have an expansion on what people call non-crossing, also planar or free cumulants. And this is something, this sort of expansion appears in several contexts, in particular in large matrix integrals, and also in free probability. So somehow, if we have an expression for these coefficients here, this gives us a certain interpolation between ordinary and free cumulants. For epsilon equal to 1, where you sum over all the genera, then you have the ordinary cumulant expansion, while for epsilon equal to 0, you are expanding on this the free cumulants. So it's really an interpolation. This would give me an interpolation between the ordinary and the free cumulant expansions. So that's a possible motivation for this work. So I won't explain you why I was particularly interested in this, in such an interpolation, but okay, that may be later. So given this, let me say what I'm going to say. I'm going to first show you a few exact results. There were not so many results, in fact, were known in the literature. And then I explain briefly the case of genus 0, which is well known. And then I'll show you how you can reduce the problem, or how you can reduce the previous diagrams to a so-called primitive diagrams. And I'm following the work of Cori and Hetyei, who were both in Bordeaux at the time, relatively recent, 2013, 2017, 2 papers. And then I'll show you how to reverse the operation, and from these primitive diagrams, recover all the diagrams. So this is what I call primitives, tracing primitive diagrams. And I'll show it explicitly for the case of genus 1 and 2. So at the end of that section, you have explicit expression for the genetic function of these coefficients. And finally, I have a few remarks if I have time. Okay, so a few exact results. So in fact, they were basically, for arbitrary genus, there were only 2 results that were known so far, which are still known, in fact, so far. The first one is a classical problem of partitions in pairs. So the problem was first addressed by Walsh and Lehmann in the beginning of the 70s. And later, Harrer and Zagier in the total. So these people were interested really in the combinatorics of the problem. And Harrer and Zagier, much later, in the mid-80s, in a totally different context, namely the study of the moduli space of curves, or specifically what they call virtual characteristics of the Euler characteristics of curves, were interested in this. They showed that it reduces to the problem of finding partitions into pairs, because that's really what it is. And they found this explicit expression. So in that case, you see, Carol, in that case, they go to the final result, okay? So they have a totally explicit expression, not only the geometric function. And another case which is explicitly known is the case in which you partition your set into 2 parts, okay? So let's say you partition the set n into, with 2 blocks of size n minus p and p. And then, thanks to a crucial observation of Philippe Di Francesco, who is here, I was able to find this explicit expression, okay, for the arbitrary genus. And the idea of the proof is, in fact, to reduce, as I'm going to explain, to reduce your diagram into something which is simpler. That would be one of these reduced diagrams that I mentioned before, and in which, if you follow the circuits, you see that you encounter alternatingly the black and the dot vertices. Okay, and then the calculation is relatively easy once you have done this. Well, not so easy, in fact, once you have done this observation. And genus 0, well, I'm going to explain in a minute. But before I do that, I would like, well, no, in fact, I'm sorry. Let's go to genus 0 first. So in the case of genus 0, there's a formula, an explicit formula, again, completely explicit, due to Creveras, and again, 72. And, well, you can see, you can look at it. It's fairly nice and it's simple. And the observation that, as far as I can see, Creveras didn't do was to, in fact, not only to look at, to compute this thing, but to return to the geometric function of these numbers. And the geometric function of these numbers has a remarkably simple expression, which is here. And in fact, in a later work with my distinguished colleagues, Brezin, Dixon, and Parisi, we made this observation, but didn't have a very good explanation of the whys of this expression. And in fact, all these things were rediscovered later by Speicher in the context of free probabilities. But in the meantime, Predrag Cvitanovic had given a very nice interpretation of this formula that I'm going to explain and that I'm going to generalize to higher genus. So what is Predrag's Cvitanovic observation? Well, suppose that I want to compute this geometric function z0 of x. So you should think of, as I explained before, endpoints on the circle. The geometric term of this geometric function has endpoints on the circle with x attached to each each point, right? Now, take a particular point, mark a point here, and look at what happens to that point. Beside the trivial point where there's no point, n equal to 0, if you have a point here, it must be attached to some vertex. Okay? So imagine that this vertex is of order n. So here I have kappa n by my rules, and then this n edges coming from this vertex, but in between you may have insertions, arbitrary number of insertions of the same thing, genus 0 things, right? So in fact, whenever you have a x, you should think of x as associated with a z0 of x. So in total, what it means is that what you have reconstructed in that way is 1 plus w, the function w. Remember, the w had no term of order 0. So that's the y of the one here. So you have w of the argument being now x times z0. Right? Do you see that? So if you accept that, I'm going to generalize that later, and you'll see that it makes life much easier. So another observation is that this equation here is in fact equivalent to something that you may have encountered if you have some familiarity with this free probability business. By a little change of functions, you can see that in fact if you introduce x, the function x, which is basically that, but evaluated at the argument y minus 1, y and, with a y minus inverse of y in front, and y of u, which is essentially this function up to a little change of variable and a prefactor, then you find easily that these two functions are functional inverse of one another. Okay? So this identity is something that people call the inverse relation in the context of free probabilities. And a related thing is that if you introduce the function y in which you remove the first term, 1 over u, then this function here is what is called Voiculescu's R function, and it has nice properties, additivity properties for free variables. Anyway, so this is not something new, and I'm going to return later to this inverse relation. So I wanted to show you that now. All right, now let me come to this point that I announced before, namely that there are this procedure of reduction to primitives, and as I explained before, I'm following the steps of Cori and Hetyei. So I've claimed that there are 4 operations that you may apply to a diagram, and which simplify it and do not affect the genus. Okay? So the first operation is obvious, it's trivial. It's a removal of singletons. It's clear that if you remove a singleton, remember how I was computing the genus, the number of faces will not change, so therefore everything else is reduced by 1, say, or by alpha, if alpha 1, if there are alpha 1 singletons, and therefore the genus is not modified. Remember this formula. Okay, so that's a trivial one. Less trivial is next step, which is to remove what are called centipedes. Namely, what I call centipede, I don't know, it's certainly not a canonical word. It's a word that I introduced. It's an insertion of genus 0, some pattern like this, with p, say, consecutive edges attached to consecutive points of the circle. Okay, so if you remove this pattern here, you are changing alpha p by 1. You're changing n by n minus p, and the number of faces. It's clear you have removed. You have lost p minus 1 faces here, and therefore the genus is not affected either. Okay. Okay, you can go on. Next step is to remove what are called adjacent pairs. So whenever you have, so here that would be one of the centipedes that I was talking about before, but look at these edges going to to points 3 and 4, for example. They are adjacent in my sense, and if I remove one of them, one of the two, clearly I won't change the genus. Again, the same reasoning. You count the number of faces, the number of points, and you find that the genus remains the same. Okay. Now you can see that because I'm going to reconstruct the graph, so reintroduce the things that I had removed. So at this point, I have to make a certain convention whether I'm removing the edge going to 3 or the edge going to 4. Okay, so there is a convention here. So I decide to remove always the edges going to the largest index. Okay, so here I'll be removing the edge going to 4. Okay, and likewise I'll be removing the edge going to 7 here in that adjacent pair. Okay, just convention. Next and last step, less trivial maybe, is the removal of what are called parallel lines. And parallel lines are pairs of edges which connect. You see, this edge connects point, the central vertex connects, say, 2 to 6, and 6 plus 1 is 7, and 7 is connected to 2 minus 1. Okay, 1. So in that sense, these two lines are parallel. And so there may be a situation in which there would be an edge coming from that blue vertex going to the external circle. Those I want to keep aside. But I remove this whenever I have this situation with at least one of the two edges attached to a two vertex, then I remove it. I remove one of the two. And again, same convention. Whenever there is an ambiguity, I remove the one which starts from the lowest index, the largest index, 2 in that case. Okay. And I didn't say it, but it's fairly obvious again to do the little calculation and to check that the genus is not affected. Okay, so when you have done all that, and you reach what Cori and Hetyei called primitive diagrams. So primitive diagrams are those in which all these previous operations have been carried out. And it's relatively easy to check, and they do that quite explicitly, to check that the result is independent of the order of reductions. Okay? So as I said, you need some conventions about which edge you remove in some of these steps, but that's being fixed. Everything is totally clear. And there is a little subtlety, as I explained also briefly. I want to keep aside the diagrams in which you have two parallel lines in previous sense, but each attached to a vertex of order larger than 2. It's simpler. I could also remove them, but the reconstruction would be more difficult, so it's better to keep them. And they called Cori and Hetyei called them semi-primitives. Okay. So now the fundamental theorem of Cori and Hetyei is that for a given genus, there's only a finite number of such reduced diagrams. Okay? And the proof is relatively easy. You notice that because of this because of the removal of singletons, the number of faces is what is it? Sorry, there's an inequality that I forgot to. No, it's here. Because of the removal of singletons, it's easy to see that each vertex is of valency larger or equal to 2, and therefore this inequality holds. And because of the removal of these parallel lines, it's also easy to see that all the faces have a length, if I can say, larger or equal to 3, and therefore when you combine these two inequalities, you find that for a given genus, the order, the n, say, must be bounded by 6 times 2g minus 1. Okay, so that's a simple and clear property. Now, an observation that Cori and Hetyei strangely didn't do is that you can now do the converse operations. Namely, reconstruct all the diagrams from these reduced ones by what I call dressing. So, of course, you have to be careful, avoiding double counting, etc. But there's a natural procedure, and for a field theorist like me, it's something which is obvious. In field theory, we are quite familiar with this sort of operation, starting from basic diagrams, Feynman diagrams, and reconstructing others in that way. So I'm going to show you in a second how to do this dressing, but as you're going to see, it works quite explicitly. For low genus, at least, you can do things quite explicitly. So let's start with the case of genus 1. Genus 1, Cori and Hetyei showed that, in fact, you have only 2 reduced diagrams. And so one with n equals 4, and the other one with n equals 6. And so as I explained, I want to mark a point to follow, to avoid double counting in the next operation of dressing. I have to fix a point, to mark a point. So the line which is attached to the mark point, which is 1, will be in red. Okay? And you see that the dressing of the red line and the dressing of the blue lines will be different. So now I want first to write an equation a la Cvitanovich, if I can say, in the same spirit as what Cvitanovich was doing in genus 0. And I claim that the Cvitanovich equation of genus 1, is here. So it has 2 terms. I'm going to explain with a picture in a minute. So there are 2 terms. One, Z1 is equal to a certain prefactor times Z1 again, plus a sum of these still mysterious dressings of these 2 diagrams. So what do I mean by that? So I've written the formula here. So consider again, same sort of reasoning as before. You take an arbitrary diagram of genus 1, and you look at what happens at marked point 1. At the marked point 1, either you have something which is connected to a n vertex, so as before. So you have kappa n times something, and the something is it looks very much like the previous diagrams in Cvitanovich equation, except that somewhere one of the what I was calling before a centipede should be of genus 1. Okay, so this is the origin of that term. This operation of selecting one point among n is just carried out by this derivative, and I have to and here I'm inserting Z1. Okay. Now the other cases is that when this xn, this mark point here, is attached to one of the lines of the reduced diagrams. Now I have to explain how to show how I want. I'm going to reconstruct all the things that are removed before. So that will be the dressing. So remember. When we had, maybe I should use 2. When I have, yeah, that's okay. Thank you. So imagine that I have a line like this, and with other lines crossing. I want to, and originally the reduced diagram, I was dealing with vertices which were 2 vertices. I didn't say it explicitly, but in this thing here, I didn't put the vertex. In here, I didn't depict a point, a dot on the blue on the red line, but there was a vertex, a 2 vertex. Okay? So now, so I have this pattern, for example, and now I want to reintroduce all the things that are removed in the previous operations. So I was removing what I was calling lines which were adjacent to one another. But because of my convention, if the point here is the mark point, I can do things here, I can attach parallel lines here, and I can also attach lines there, right? That's because by my convention, I always keep the edge which is attached to the mark point 1. Okay. In contrast, if I want to do the dressing of the other lines, here, for example, for that one, well, I should do that maybe on a different thing. So if it's not the marked point that I want to trace, then excuse me, from this point I can attach things here and I can attach things there, but I'm not going to attach things here. So I have a smaller tracing, if I can say, than in that case. Okay, so that will explain why I have different powers. 1 minus, so that will be the edge attached to the marked point in red, an edge attached to the non-marked point, and there will be a 1 minus x 2 to the square. Because I have an arbitrary number of things, I reconstruct a geometric series, and therefore things are just become things in the denominator. Okay? And no, I'm sorry. Here, excuse me, I take it back. What I'm showing you here is the difference between the numerators of these expressions. So here, I have to choose 3 locations among k. So this gives me this prefactor here. While here, I have to reconstruct that will be in that case. In that case, then I have only a prefactor. I have only a prefactor k minus 1. Anyway, so this sort of things is always a bit difficult to explain on a blackboard. I hope you follow me, or at least you believe me, you trust me. Now, in addition to that, as explained also before, you have to reintroduce what I was calling parallel lines. And parallel lines, in that case, would be an arbitrary number of lines in that way. Okay? Each one would be, again, originally attached to 2 points, but again, by the same argument, you could dress it itself with a factor x2. So it will be a sum of x2 to the k, from k equal to 0 to infinity, whence this 1 over minus x2 that you see in several places. Okay? So, and once you have done that, you are not yet finished, because remember, the first thing I did in the previous reduction was to remove what I was calling the centipede. And centipede was insertions of subdiagrams of genus 0. And that will be taken care of by, in the next slide, by everywhere replacing the variable x by x times z0. Again, that we encountered already in the discussion of Sitanovich equation. Okay, so if you believe me, if you trust me, at the end of the day, you have found that Z1 is, there was Z1 appearing on the left-hand side and the right-hand side, and on the right-hand side, it was coming with this derivative, right, of W. So that, this is what I call now V. V is this x times the derivative of W. And, excuse me, and so this is why it appears in the denominator. And finally, you find this expression for the geometric function of genus 1 partitions. Okay? Did you follow? If you say yes, I won't believe you. Anyway, this formula, of course, I checked with all possible knowledge that I had. I had, of course, collected as many data as possible, going to partitions up to n equals 13 or 14, I forgot. Anyway, so I had a lot of data, and I could check that. Also, I checked that against the 2 cases, the 2 exact formulae that I showed you before, these partitions into pairs, or the partitions into 2 parts. So this formula passes all the tests, of course, otherwise I won't be here explaining you that. Okay, next step, going to genus 2. So if you found the case of genus 1 a bit intricate, to be even worse for the case of genus 2, because you have many more diagrams, many more reduced diagrams, again a finite number. But you see, these things have been tabulated by Cori and Hetyei, and I rechecked everything, so I agreed with all their data and numbers. And you see, there are there are a finite number of vertices, and of course a finite number of possible vertices, finite number of reduced diagrams, I'm sorry, and of course a finite number of vertices involved. So you may have only 2 vertices, or you may have 1 3 vertex, 2 3 vertices, etc. So a finite number of cases. And patiently, you carry out all this operation of tracing that I was explaining before. And when you do that, so here is a little sample of diagrams. So those are the 52 primitive diagrams with 7 into 7 pairs. So at n equals 14. So that was this. Where is it? This 52. Where is 52 here? Excuse me?
In the very middle.
The middle column in the middle.
Oh yes, here. Thank you. Here it is. Yeah. And yeah, 52 primitive diagrams with. This is incorrect. This is not 2. Yeah. Anyway, I don't understand. No, sorry. It's not. Excuse me. It's not 52. It's those are the number of independent diagrams, but of course each one has to be rotated. So you have in fact to count the total length of the orbits of these things on the rotation. Okay. So if you do that, you find that total weight is 651, which is here. Okay. Okay, and likewise, here are 3 semi-primitive diagrams just to show you what these semi-primitive diagrams look like. Anyway, so you have all these things, tabulated all that. It's even available on my website. And at the end of the day, when you reconstruct everything, you have this horrible formula, horrible, but quite explicit. And again, you can expand that to any order that you like and check it against all the data that you have. And of course it works. And against the 2 exact cases that I showed before. So these formula are quite nasty, but they are correct, I think. Okay?
So what is S?
S, where is S?
Z2, Z3, Z10.
Yeah. I'm sorry. That was referring to my previous list of diagrams. So here I had 5 categories, if you can say, of diagrams. Some of them being with 2 3 vertices being semi-primitive. Okay.
So this is semi-primitive.
S for semi-primitive. Yes. Thank you for the question. I should have said that. Okay. So
10 minutes, is it possible?
Oh yeah. Quite so. So just an example of a formula which is new. What I call higher genus Fus Catalan. So imagine that only one of the kappas, the variables that I was attaching to vertices, only one of them is non-zero, namely kappa 3. This means that you allow only 3 vertices in your diagrams. Okay? So if you look first at the case of genus 0, then you have to solve this equation. And this is a well-known case. And this is the generic function of the Fus Catalan numbers. Okay? And I wrote it in that way. The trigonometric equation, solution of this cubic equation is apparently the best way of doing things. And when we carry out the next steps that I was showing before, you find this explicit, relatively complicated, but still explicit formulae. Okay? And again, I check that. And notice that there are this denominator, this term reappears in the denominator with different powers. And likewise, here you have a common factor. And also, I could also do something similar, namely give the same value to all vertices with or without kappa 1, namely keeping or removing the singletons. And then I'll be exactly on the ground that Carol was discussing this morning before his specialization, namely compute the Bell numbers, but for genus 1 or 2. Okay? And likewise, I could also fix the number of parts, and that would be the Stirling second kind, but genus-dependent Stirling numbers. Okay? So everything of that type can be done. In fact, these things had been done before by Cori and Hetyei as a result of their discussion, they had these numbers. So I checked that, I reproduced the results, and so everything seems to be all right. Now, let me come to something which is fairly new and quite intriguing. After I posted my paper, because the second paper is slightly different, after I posted my paper, I received a mail from a young guy in Oxford, Alex Hock, apparently a young German fellow, a postdoc at Oxford, who made a very curious, very empirical, but quite amazing observation on these results. Namely, using what himself is a specialist of what is called topological recursion. So he's quite at ease with all these relations developed by Hénard, Orantin, Chekhov on connection discounting for different genera. And also making use of this observation that I was doing at the beginning of the talk, namely this inverse relation. Remember that there were a little reshuffling of the two generic functions Z0 and W, which had this property of being inverse of one another. X times Y or Y times X is the identity function. So he suggested to re-express all the previous results in terms of the function capital X of Y. And he found this expression, which, well, at this stage, it's not so much simpler than what I had myself, but look at the result that he has for genus 2. Here, there is clearly a simplification, because there is a pattern. If you look at things, the first line has a series of a sum of fractions with increasing degrees of y and the first derivative of x, and the second line has a triple derivative of x over some denominator with a minus sign here, etc. Okay, there is a pattern. For him, it's just empirical, but it make you think, right? Suggests that there is something, and of course, he made immediately a conjecture of what should be the similar formula for higher genus 3. He had something like 80 or 90, I forgot, coefficients, which for him are still to be determined. Okay? So what is missing in his approach is to understand by a different approach, a direct approach, what is the meaning of these coefficients. If he had that, he would have a much simpler approach to this problem of counting. So I think there is some room for some further work, and I'm coming to the last transparency. The question is whether this famous topological regression is at work. I don't know. Anyway, open problem. Last slide, final remarks. Well, I made already the observation on the case of the, excuse me, on the case of the Fuchs-Catalan, genus-dependent Fuchs-Catalan numbers. There is a common feature that appears again and again, which is that there seems, in all these countings, there seems to be a universal singular behavior. Whenever you have a single type of vertex, like in partition into pairs, or partition into triplets, like in a Fuchs-Catalan, or in these Bell numbers, where you have only one variable, you can see it explicitly. For genus 1, genus 2, and for some reasons we have also, we know, of course, in the case of genus of partition into pairs, we know this formula quite explicitly. There is some universal singular behavior. Namely, all these partition functions have a singularity with a certain power, half minus 3g, which seems to be universal. And this would imply that when you look at the large n behavior of the corresponding coefficients, then they should behave with this sort of behavior, say, okay? So why is that so? So I've been discussing that with various colleagues, combinatorics or string theorists, and all say, oh yes, it's natural, we expect that. So maybe you have your own explanation, but for me it's still another fairly mysterious thing. And finally, there is still this problem that I was mentioning before. The possible role of topological recursion in this problem of counting is still open. I've been asking several specialists, and they say, oh yes, interesting problem, but we don't know. So maybe one of you has something to say on that. Thank you very much for your attention.
Yes, Andrea.
Andrea, you have understood everything as usual.
Well, I follow with the question.
Okay, very good.
Did you talk already to Guillaume Chapuis, you said?
Yes.
And he didn't mention his work on Toda, KP, and all those stuff.
And Toda?
Toda hierarchies in maps.
He showed me that the problem that he had solved, if I understood him correctly and if I remember correctly, were parallel to that, but as far as I remember, he didn't say that he had a different approach. Are you saying that he was talking about counting of hypermaps and these kind of things? But explain.
He has a different approach to Eynard Orantin, which is more based on integrable hierarchies, KP, I suppose,
KP.
and also Valentin Bongon is doing that a lot. And this frames all those higher genus but finite genus formulas into something that solves differential equations, which are the KP equations. And so they seem nasty, but after that you rearrange them, the KP equation is much more compact. I believe that there is something in this direction.
It didn't show me that. We didn't discuss that. We discussed more on the singular behavior, these kind of things. And but I don't think he discussed that. Yeah. Okay. Interesting.
And he's the expert. I'm not.
Okay. Yeah. Okay. Thank you.
Other questions? Yes, Parek.
So thank you. Now I remember that before Voiculescu, before free probability, which I also work, were papers on free product of groups done by Wolfgang Wess, and he proved Voiculescu before Voiculescu even, that equation what you wrote, what we call moment cumulant formula, yeah, and he found just in your spirit, I think, but that paper is 80s. Wolfgang Wess, you can see, and he worked in probabilistic way, so he considered like random walks on graphs, or free product of graphs.
Yes.
And my question is, if you also, because of course you are coming to final result, but before this was something, yeah, like random walks, like a random matrix. So it will be interesting to see that of the result, which we forgotten now, because we come now to formal language, cumulant, free cumulant, what you call kappa and yeah, and so on. But that random walks, I think random walks was Kesten teach me, I remember, and I'm under impression that people forgotten about random walks.
Not everybody.
But this is the language of random walk, no? You don't experience that your constant genus should be in random walk. When you paper Zagier and Harrier, this was in the spirit, no? Or you don't see that this is some kind of random walk.
You have no
maybe
insight.
multi-dimensional, no one-dimensional, maybe not on tree, maybe on buildings, street building or something, no?
You have more insight than me. Thank you for the comment anyway. Yeah. Wess, you said it.
Wolfgang, yes, yeah.
Okay. Thank you.
Okay, we thank the speaker again.